Hey everyone, as always I hope you're having an amazing day. In this video we're going to do a quick introduction to energy and metabolism. We're going to start off by talking about organisms and how they're categorized based on how they obtain energy in carbon molecules. We're then going to talk about different reactions when referring to metabolism. We're then going to talk about Gibbs free energy, and we're going to end this video off with potential and kinetic energy. So let's get started. Now, when it comes to organisms, they can be characterized into two major groups based on how they obtain energy. They can either be phototrophs, where they obtain energy from sunlight, or they can be chemotrophs, where they obtain energy from chemical compounds. Now, these can also be further broken down based on how the organism obtains its carbon molecules, which can be used to make larger molecules. Autotrophs obtain carbon from inorganic sources such as CO2, while heterotrophs obtain carbon from organic compounds. Now, a good way of classifying this is autotrophs are usually seen as producers, while heterotrophs are seen as consumers. So a good example of an autotroph is plants, while a good example of heterotroph is humans. So you can have a photoheterotroph and you can have a photoautotroph. Similarly, you can have a chemoautotroph and a chemoheterotroph. Next, we're going to talk about reactions when referring to metabolism. Anabolic reactions are reactions in which smaller molecules are put together and turned into a larger molecule. Now, this requires an addition of energy. When you add energy to a reaction, this is called an endergonic reaction. Another type of reaction found in metabolism are catabolic reactions. Catabolic reactions is a reaction in which a larger molecule is broken down into smaller molecules, and in the process, energy is released. Now, when energy is released in a reaction, this is called an exergonic reaction. So anabolic reactions are endergonic reactions because energy is added, while catabolic reactions are exergonic reactions because energy is released. Now, what is Gibbs free energy? Gibbs free energy is the amount of free energy available to do work in a reaction. Delta G is the change in free energy between products and reactants of a reaction. Basically, Gibbs free energy is a way for us to know if a reaction is spontaneous or non-spontaneous. Now, what this means is if a reaction will go forward without the addition of energy, or if we're going to have to trigger the reaction. So if a reaction will go forward without any addition of heat, then the reaction is said to be spontaneous, while a reaction that is non-spontaneous requires the addition of energy. We need to trigger the reaction. Now, how can we tell if a reaction is spontaneous or non-spontaneous based on this equation right here? Well, if delta G is negative, then the reaction is spontaneous, while if delta G is positive, then the reaction is non-spontaneous and requires the addition of energy. Let's look at this equation a little more closely. So as we said, delta G is a change in free energy. This is equal to delta H, which is the change in enthalpy. What this means is the change in heat of the reaction, minus T, which is the temperature, always measured in Kelvin, times delta S. Delta S is the change in entropy. What is entropy? Well, entropy is the measure of disorder. The more disordered something is, the more entropy it has. A good example of this is if you look here, this is tidy and this is messy. The messy has more entropy than the tidy. If we want to go from messy to tidy, we need to put in energy. If you want to think of entropy in molecules, the atoms in solids are said to be organized. They're next to each other, close, clustered, while gases are further apart and more random. So gases have more entropy than solids. What is delta G naught? Delta G naught is the standard free energy change. What this means, it's the free energy change under standard conditions, those being all reactants and products being at an initial concentration of 1 molar, pressure at 1 atm, and temperature at 25 degrees Celsius. Now, when we say, will a reaction go, you're going to hear this phrase a lot. This is basically referring to whether the reaction is spontaneous or not. So if a reaction goes, that means the reaction is spontaneous and delta G is negative. If you look at the second equation here, R is the gas constant, which is a constant value. T, again, is temperature, times the natural log of K, which is the equilibrium constant. So the concentration of the products over the concentration of the reactants. Here we have two reactions, one exergonic and one's endergonic. If we look at this reaction to the left, the amount of free energy in the reactants is more than the amount of free energy in the products. That means in the process of this reaction, energy must have been released. This means that it's an exergonic reaction as energy was released. Since delta G is less than 0, this means this reaction is spontaneous, so it will go ahead without the addition of any energy. If we look at this reaction on the right, the amount of free energy in reactants is less than that of the products. Therefore, delta G is less than 0, making this reaction non-spontaneous. Since the amount of free energy increased from the reactants to the product, that means energy must have gone into the system, and therefore this reaction is endergonic. So if we want this reaction to take place, we need to put in energy, as this reaction is not spontaneous. Lastly, we're going to talk about the potential and the kinetic energy. We're going to talk about them together because they go hand in hand. Together, potential energy plus kinetic energy make up what is called the mechanical energy. We'll talk about that more when we talk about the laws of thermodynamics. Potential energy is said to be the stored energy of an object because of its position or state, while kinetic energy is the energy of an object due to its motion. If you look at this image on the right here, when the biker is at the top of the hill, his potential energy is highest. This is because relative to his position, the amount of stored energy is the greatest. While the biker goes down the hill, down here, kinetic energy is at a maximum. This is because the biker is at the largest velocity. As the biker goes down the hill, potential energy is decreasing while the kinetic energy is increasing. Down here, potential energy is 0 while the kinetic energy is at a maximum. Now, to get to this high of a potential energy was required. The input of energy was done in this case as work. The biker put in energy to get to the top of the hill. This relates to physics, so we won't be going in depth, but this is the general idea. You put in energy to get to a higher potential energy, and once the potential energy is turned into kinetic energy, potential energy goes down while kinetic energy goes up. They go hand in hand together. We have reached the end of this video. I really hope it was helpful, and I hope you have a great rest of your day.